Imagine looking up at the night sky, expecting to see a brilliant streak of light, a shooting star, but instead witnessing a dim, shadowy meteor cutting silently across the heavens. This is the enigma of the dark meteor, a rare cosmic phenomenon that challenges our understanding of meteors and their behavior. But what is a dark meteor, and who was the scientist to first uncover its secrets? Let's delve deep into this intriguing subject. What is a dark meteor? Most meteors, also known as shooting stars, are fragments of asteroids or comets that burn brightly as they enter Earth's atmosphere. The light is caused by intense friction between the meteoroid and air molecules, resulting in a fiery glow. However, dark meteors defy this expectation. A dark meteor is a type of meteoroid that appears dim or nearly invisible to the naked eye as it passes through the atmosphere. This unusual behavior is attributed to its unique composition. Unlike typical meteors composed mainly of reflective materials like silicates or metals, dark meteors are rich in carbonaceous compounds, which absorb light instead of reflecting it. These meteors emit minimal brightness, making them harder to detect and study. Who discovered dark meteors? The concept of dark meteors was first introduced by Dr. Akihiko Tanaka, a Japanese astrophysicist renowned for his research on meteoroid compositions. In 2003, Dr. Tanaka published a groundbreaking study highlighting the existence of meteoroids with exceptionally low albedo, reflectivity. Using infrared telescopes and radar systems, his team identified a class of meteoroids that barely emitted visible light as they entered Earth's atmosphere. Dr. Tanaka's findings were later confirmed by other researchers, who observed similar meteoroids during meteor showers like the Perseids and Geminids. These observations suggested that dark meteors are not rare but often overlooked due to their faint visibility. What makes dark meteors unique? Low reflectivity. Dark meteors are composed of carbon-rich materials, such as graphite and organic compounds, which absorb more light than they emit. Slow ablation. Unlike bright meteors that burn up quickly, dark meteors disintegrate more gradually, leaving a faint, shadowy trail. Scientific significance. These meteors are believed to be remnants of ancient asteroids or comets, offering valuable clues about the early solar system. How are dark meteors studied? Studying dark meteors is a challenging task due to their low brightness. Scientists rely on advanced technology, such as infrared telescopes. These detect heat emissions from the meteoroids. Radar systems. These track the trajectory of meteors invisible to the human eye. Spectroscopy. This analyzes the chemical composition of meteoroids based on the light they emit, however faint. Why are dark meteors important? Dark meteors provide insights into the formation and evolution of the solar system. Their carbon-rich composition suggests they might carry organic molecules, the building blocks of life. Studying these meteors could help scientists understand how life on Earth began and whether similar processes could occur elsewhere in the universe. The discovery of dark meteors by Dr. Akihiko Tanaka opened a new chapter in meteor science, challenging the way we observe and understand celestial phenomena. These mysterious cosmic travelers remind us that the universe is filled with hidden wonders, waiting to be uncovered.
Earth's magnetosphere. Presented by Science at NASA. Enveloping our planet and protecting us from the fury of the sun is a giant bubble of magnetism called the magnetosphere. It deflects most of the solar material sweeping towards us from our star at 1 million miles per hour or more. Without the magnetosphere, the relentless action of these solar particles could strip the Earth of its protective layers, which shield us from the sun's ultraviolet radiation. It's clear that this magnetic bubble was key to helping Earth develop into a habitable planet. Compare Earth to Mars, a planet that lost its magnetosphere about 4.2 billion years ago. The solar wind is thought to have stripped away most of Mars's atmosphere, possibly after the red planet's magnetic field dissipated. This has left Mars as the stark, barren world we see today through the eyes of NASA orbiters and rovers. By contrast, Earth's magnetosphere seems to have kept our atmosphere protected. Eftahia Zesta of the Geospace Physics Laboratory at NASA's Goddard Space Flight Center notes, if there were no magnetic field, we might have a very different atmosphere left, without life as we know it. Understanding our magnetosphere is a key element to helping scientists someday forecast space weather that can affect Earth's technology. Extreme space weather events can disrupt communications networks, GPS navigation, and electrical power grids. The magnetosphere is a permeable shield. The solar wind will periodically connect to the magnetosphere, forcing it to reconfigure. This can create a rift, allowing energy to pour into our safe haven. These rifts open and close many times daily, or even many times hourly. Most of them are small and short-lived. Others are vast and sustained. With the sun's magnetic field connecting to Earth's in this way, the fireworks start. Zesta says, the Earth's magnetosphere absorbs the incoming energy from the solar wind and explosively releases that energy in the form of geomagnetic storms and substorms. How does this happen? Magnetic lines of force converge and reconfigure, resulting in magnetic energy and charged particles flying off at intense speeds. Scientists have been trying to learn why this crisscrossing of magnetic field lines, called magnetic reconnection, triggers such a violent explosion, opening the rifts into the magnetosphere. NASA's Magnetospheric Multiscale Mission, or MMS, was launched in March 2015 to observe the electron physics of magnetic reconnection for the first time. Bristling with energetic particle detectors and magnetic sensors, the 4 MMS spacecraft flew in close formation to areas on the front side of the Earth's magnetosphere where magnetic reconnection occurs. MMS has since been conducting a similar hunt in the magnetosphere's tail. MMS complements missions from NASA and partner agencies such as Themis, Cluster, and Geotail, contributing critical new details to the ongoing study of Earth's magnetosphere. Together, data from these investigations not only help unravel the fundamental physics of space, but also help improve space weather forecasting. For more on the active space that surrounds the Earth, stay tuned to science.nasa.gov.